Alrighty, CNT140, we're looking at Chapter 8, and we just got done talking OTDRs. Now we'll move on to testing long-haul, high-speed fiber and optic networks. They remind us, yes, big advantage of fiber optics, long distance, high speed. Attenuation is lower at longer wavelengths, lower attenuation. Single-mode fiber has very high bandwidth. Fiber can be fusion spliced with virtually no loss, so you can have long distance cables with little loss. That's one of the advantages, of all of our fiber optic. Now with long distance, there's new factors in performance that come into play. Chromatic dispersion. This is the dispersion caused by light of different wavelengths. Remember we talked about if you send light through a prism, it breaks out into component pieces. As you start sending light down a fiber and it starts bending in and out of the core, it can start breaking into those component pieces, and your pulse of light can start spreading out, oozing out, and getting larger. Polarization mode dispersion. Remember, as we send light down through a fiber, it's actually made up of two component parts, kind of at right angles. Well, as they move down through the fiber, the core and cladding, some of the component part could actually start spreading out or lagging behind as it goes down through the fiber, and now your signal again is spreading out as it gets to the other end. And attenuation with wavelength. Yes, different wavelengths attenuate differently. This can be a factor when you're working with wavelength division multiplexing. You have different wavelengths there. So your signal could spread out with those different wavelengths. As network speeds increase beyond 10 gig and distance become more than 20 kilometers, it's important to test your single mode fiber, outside plant fibers for bandwidth. For older cable plants, you might be trying to upgrade bandwidth, so you need to know, is this capable? To know, will this actually carry what we're trying to do? Newer installations, we want to know, will they support speeds higher than 100 gig? And things like dense wavelength division multiplexing. So there's some additional tests we're going to do on these long outside plant fibers, if you will. Chromatic dispersion, polarization mode dispersion, and spectral attenuation. These are all lumped under the heading of like fiber characterization. Highly specialized, requires special equipment. Yeah, we don't have equipment for this. We're just going to get familiar, at least recognize some of the terms. We should remember chromatic dispersion. As the light pulse moves down through the fiber, it starts bending and breaking into component pieces. So on the other end, these component pieces start spreading out, making that light pulse longer, if you will. That's your chromatic dispersion. So testing there's several methods but it actually involves testing at a variety of wavelengths using several discrete sources and wavelengths and measuring the relative speeds of those signals. Data is then taken at the discrete wavelengths and then analyzed to calculate dispersion in terms of, here's a new measurement, picosecond per nanometer per kilometer. And a picosecond is 1/1 trillionth of a second, if I remember correctly. Yeah, 1/1 trillionth of a second. So you might have a couple pico, I think I have over here. Yeah. So if we have here picosecond per nanometer per kilometer, 1 picosecond is 1 trillionth of a second. So picosecond is 1 trillionth of a second. And you might actually have down here, I think there's the example. For every kilometer of fiber traveled through a pulse within 1 nanometer spread of wavelength will disperse by 1 picosecond. Then that gives you your 1 picosecond per nanometer per kilometer. And again, we're talking long distances. These come into play, so they need to be measured for. And this even shows you the source and then the reference coming back. OTDR can be used to test for this, because an OTDR measures time to convert to distance, and the speed of light is different at various wavelengths. So the OTDR would measure different lengths of fiber at different wavelengths. So, it sends a pulse down. I'm just going to use a generic color red. It's going to measure the cable is so many meters long. Blue, it's going to be maybe slightly longer. Green, it might be slightly longer. So that would let you know the amount of dispersion when the cable hasn't changed length, but those wavelengths light are indicating it's a different length. That's one way that you could test for that. Test traces are taking several discrete wavelengths and then calculate the difference between those. And it's this idea right here. As I'm doing here, red shows it this long, yellow this long, green this long, and you can basically compare those to know how much dispersion you got from that by indicating the cable's different lengths. Here's a bunch of test standards for testing for chromatic dispersion. I think they have this in the book as a chart for you. Polarization mode dispersion. Remember, as we send light, send light down through fiber is actually two component pieces at right angles. And with that, some of your materials, glass, optical fiber, have different index of refraction on each of those components, and that is called birefringence. So each component of polarized light travels at a different speed, causing dispersion then. So as it's moving down through one fiber to the next, it's encountering these different indices of refraction. Those component pieces might travel at slightly different speeds, if you will, or bend at different amounts, and that would affect the signal. Those component pieces would get affected, creating dispersion. This right here says it comes into play with long concatenated fiber, where I have one fiber joined to another fiber joined to another fiber. There might be micro differences in them, and that can create this birefringence characteristics. These are particularly noticeable in aerial fiber, where you have a lot of bending and twisting in the fiber, but also temperature and wind, causing some variations in this. So that can cause some polarization mode dispersion. It's tested during manufacture, in the field, newly installed fibers, or when upgrading fibers. And your polarization mode dispersion can vary over time. So any tests that are done are usually compared to or average to previous ones. Here shows you, again, different methods used for and the magnitude of your polarization mode dispersion is referenced as DGD, differential group delay, and called typically delta tau, using two of the Greek letters delta tau, change, the delta is usually like a change in. And then here's a bunch of different methods to test for polarization mode dispersion. They talked about with this, there's a number of different tests. Some of them are kind of uncertain, and they're saying some of these might not be too reliable, but it's still worthwhile to test because they're still getting information out of it, and as they're learning more as they go too. And they also did notice that in here, variations can be correlated to wind or speed for aerial cables, and even vehicles and trains passing by underground cables can affect this because pressing on the ground and so forth. So it still needs to be done on these long links, but it needs to be analyzed intelligently by somebody trained to do this, and be aware of some of these things that cause or affect. Spectral attenuation. If you remember the development of low water peak fibers, this allows transmission in the 1260 nanometer to 1675 nanometer wavelengths, allowing things like wavelength division, multiplexing, and so forth. Water peak fiber, the careful manufacturing of fiber optic comes into play to reduce the amount of water in the fiber in the form of these ions, hydroxide ions, that causes a lot of spectral attenuation around 1244 and 1383. So if I look here, typically there was a lot of attenuation at these wavelengths. In regular fiber, we have a lot of attenuation, so those tend to be avoided. But your low water peak fibers minimize that, allowing a bigger range of wavelengths to be used for things like coarse wavelength division multiplexing and dense wavelength division multiplexing, allowing those two to happen. So if you want to use a fiber of unknown spectral attenuation, you would need to test for this to see, is it suitable? Is there too much attenuation at these wavelengths, to know whether you could actually use this for wavelength division multiplexing of various sorts. Legacy fibers may have attenuation coefficients of 2 decibels per kilometer. Your low water peak might be down to 0.4 decibels per kilometer. And again, allowing transmission in these wavelengths to allow for your wavelength division multiplexing. And here's the output of your tests, and then the attenuation of the fiber calculated from those tests. And they mentioned some other testing that might get done. A lot's done by the manufacturer to make sure things are within parameters for the user, and it's done before shipped to customers. Things like the dimensions of the fiber core cladding, the how oval is it, how circular is the fiber, that sort of thing. Performance, attenuation coefficient, bandwidth, dispersion, that sort of thing. Physical characteristics, strength, flexibility, how much can it bend, ability to withstand environmental conditions and sometimes over lengths of time. So all those things would be done and are tests that are making sure that cable is suitable for what we want to try to use it for. They also test connectors and splices, large batches, and kind of average them out to know what's expected. Environmental testing, including vibration for use in vehicles, ships, aircraft, that kind of thing. And even your electronic components, transceivers, your small form pluggables, those sorts of things, and wavelength division multiplexing, amplifiers, all those to test to know, are they performing to the level that they should be? Those are all tested, usually the manufacturer's doing for us. So there's a whole bunch about testing from Chapter 8. We'll be using the visual fault locator, the microscope, the power meter, and I even have it's kind of like a polarity meter to check, is the fiber optic link working as it should? So there's a bunch of things we'll be doing in the lab for this chapter.